Hello, ladies and gentlemen. This is Mr. Hunter, and this is your electrodynamics notes part 2. So last time we talked about electric fields and how a voltage is work done over a charge. We talked about current, and we also talked about uh, resistance. And so now we're going to talk about voltage real quick. So voltage, or another word for voltage, is your potential difference, is the ability to push electrons. So remember we talked about if I were to get if I was to get charges to flow through a wire, I would need a potential difference. Why? Because electrons hate electrons and they like protons. And so if I want electrons to move through this wire, I need to add a potential difference or a voltage between the two areas. So that's our potential difference, right? And so think about all your batteries. Your batteries, you have a positive and negative side, and that's because you're trying to create a link between a positive and negative in order to get charges to flow. Now, remember, as I stated in class, we always say that electrons flow from positive to negative, which doesn't make sense because negatives don't like negatives and positives like negatives. And we kind of keep that convention in honor of Benjamin Franklin, because when he modeled this, he kind of had it backwards because he understood some of the concepts. But as he stated, we can't see electrons or protons. So we kind of had the convention backwards. So our potential difference is the ability to push electrons. And there's two ways to find it. We have voltage equals current times resistance, which is Ohm's law. And that's how we can find the voltage. Or there's another equation that I showed you earlier where we can have, let's see, voltage is equal to work. In this case, it's kind of like electrical work. It's divided by Q, and remember, work is force times distance. So in this case, it's called the electrostatic force times the distance, and that's divided by how much charge it is. Because think about it. If I have a charge in an electric field, if they're the same charges, if I have two positives, remember I discussed before that I have to do work to make those charges move closer to each other because they don't like each other. Now, another thing that we will deal with is relating to electric power. Now, remember, the original equation for power, which happens for physics in terms of mechanics and moving stuff like lifting a box in a certain time, or like you guys running up the stairs, is power is work over time. So this still stands true for electrical power. So electrical power, if I solve for work equals, let's see, power times time. Which when you look in your electricity section at the very bottom, you'll see a bunch of different equations for work and electrical power. But power, and remember, power is energy per unit time. So we're talking about electrical power is voltage times current. It is also equal to the current squared times the resistance, and it's also equal to voltage squared divided by resistance. And so that's how much power that the circuit that we're going to be talking about momentarily is consuming. And all of those equations are found right on your reference table. I'm actually using your reference table as I write these equations. Now, if you flip over to the back, now I want to talk to you about series and parallel circuits. We've talked about electrostatics, which is electrics like charges, kind of free form, and electrodynamics is the movement of charge, which also entails the movement of charges through wires. Now, please remember, you have to have a complete path from positive to negative in order for charges to flow. So you have to have a complete, scroll this over, you have to have a complete path in order for charge to flow. And by a complete path, I mean from positive to negative. So when we mean a complete path, we mean from positive to negative. Remember in class, I showed you guys, like, if I were to break that wire, then I basically wouldn't get charge to flow because it doesn't see that potential difference. It doesn't see that negative on the other side. Why? Because essentially broke it off. So it only has a positive. There's no way to complete the path. So a series circuit is a circuit where electrons can only go in one path. And there's different ways to say it, but it's basically a circuit where electrons can only take one route, one path, right? And just to let you know, as I'm talking about it, electrons, this is my statement, electrons are a lot like students. They take the path of least resistance. What I mean by that, if you think about you guys, you do the minimal amount of work you can do to get the most amount done, or some of you it's just like, okay, I'm going to do this amount of work because this amount is passing. But some of the students are like, I want an A, so I'm going to put in that much effort I need to get an A. So electrons take the path of the least resistance. Electrons take the path of the least resistance. So if I have a path that's high resistance and a path that's lower resistance connected to the same point, some electrons will still go through the high path, but a majority of the electrons will still go through the easier path. So for example, like equating it back to students, students that are typical A students are those electrons that go through that harder path. Why? Because they want a better grade, so they put in more effort to make sure that they have that A. Where some students are like, I don't care, I'll just pass, and so they do the least amount of the work that they could do to just pass. Now, one thing that we're going to start drawing as well is something called the schematic view. So in your reference table on the bottom left is a circuit symbol, and so now to draw circuits, we're going to use those circuit symbols because they're a lot easier to draw than drawing like what we did in your resistance and wire lab, where you draw like the actual what it looks like. So you draw a wire and you draw a box and you connect it different wires. So this is called a battery. So series circuit, so now I'm going to draw a battery, and I'm using also your reference table. So that's a battery. The long side is positive, the lower side is negative. So a series circuit is like, let's just put, it's only one path where electrons can flow. So I'm going to put a switch in, and then I'm going to put in a resistor, and then let's put in a lamp. And a lamp is like a little squiggly with a circle around. So in here I have a lamp, resistor, and a switch. And if you notice, when you trace the path, the electrons can only go one way. So once I close the switch, they can go through it, they go through the resistor, and the energy will light up the light bulb, and we'll actually build one of these in class. So because I'm getting short on time and want to introduce this, at least both circuits to you, I'm just going to quickly give you the equation, and then the next video I'll go into the equations and why they are. So my total current equals the current in the first part equals the current in the second part equals the current in the third part, which I'll get to why that is later. And then voltage equals the voltage across the first thing plus the voltage across the second thing plus the voltage across the, so the total voltage is all the voltages added up, and the total resistance is going to also be the resistances added up. And in the next homework video, I will explain and go into why that is. Now, a parallel circuit is opposite of what the series circuit is. So a parallel circuit is where electrons can take multiple paths. So electrons can take multiple paths. So here's what it looks like, right? So here I'm going to draw my battery again. And remember, here's my negative because it's smaller, and here's the positive side because it's longer. And so electrons get to here, and they can split up and go through here. And then they can also split and go through here. So this is a parallel circuit, because think about it. Electrons can come in here, and they would split to go to this resistor, which we'll call R1, and then they can also split down here and go this way and go through what we call resistor 2, and then they combine back together and come back. And so, because I want to keep this video short, I'm going to just give you the equations, and then in the next video and probably in class, we'll go over why these equations are the way they are. So, our total current is equal to the addition of the currents that are available in each of the parts of the circuit. Our total voltage will actually equal the voltage in each part. And just very briefly, the reason why that is because like all of those parts of the circuit are connected directly to the battery. And then we have total resistance is actually equal to, actually it's 1 over total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, which if we were to rewrite that and solve for R1, RT would actually be, I rhymed, 1 over R1 plus 1 over R2 plus 1 over R3 is another way to write that equation if we were to solve for total resistance. So, in a nutshell, that is series and parallel circuits. Remember, parallel is where electrons can take multiple paths, and series is where they can only take one path. So these notes will be due when I said they were due in class, and I will check them, and we'll have some work that is related to this. Have a good one.